Welcome. Microhybrid would like to introduce you to the NDIRsim app. NDIRsim runs directly in your web browser on any operating system, so you can simulate NDIR gas sensing without installing any software. NDIRsim uses the HITRAN database to model gas absorption. HITRAN is a scientific reference database containing highly detailed data on how gases absorb infrared light across a wide range of wavelengths. In this video, we'll guide you through the full process. You'll learn how to select the gas you want to measure, set temperature and pressure, and define all the key parameters needed to generate a response curve. Let's get started. Part 1 of 3, Defining Gas and Conditions. Step 1. Start by entering the gas you would like to measure in the field labeled Gas. For today's example, we'll choose CO2. Step 2. Next, enter the gas temperature in the temperature field. In our example, we'll use 37 degrees Celsius. You can also enter the temperature in Kelvin. When you enter a value in one unit, the app automatically displays the corresponding value in the other. Step 3. Now enter the pressure inside your gas measurement module in the pressure field. We'll use 1 atmosphere. You can also enter pressure in millibars. Again, whichever unit you enter, the corresponding unit is calculated and shown automatically. Step 4. Define the spectral range you want to evaluate by entering the minimum and maximum values as either wavelength or wave number. In this example, we'll set the range from 4,000 nanometers to 4,500 nanometers. The app converts between wavelength and wave number automatically, so both views stay consistent. Step 5. Choose the number of sampling points. Sampling points are the discrete grid points where the app calculates values such as absorption coefficient and transmittance across your selected spectral range. More sampling points provide finer spectral resolution, while fewer points calculate faster but can reduce accuracy and affect the predicted signal. For our example, we'll enter 1001. Step 6. In the volume percent field, enter the maximum concentration you want to simulate in volume percent. We'll use 5 volume percent. If your concentration is given in ppm, you can convert it to volume percent by dividing by 10,000. For example, 50,000 ppm equals 5 volume percent. Step 7. Click Draw Diagram to display the spectrum. Depending on the automatic y-axis scaling, strong absorption peaks may appear clipped. That's normal and usually not critical. What matters more is that your spectral range includes enough space on both sides of the target absorption band so you can evaluate usable regions, for example, for filter placement or reference areas. The y-axis shows the absorption coefficient, which describes how quickly infrared intensity decays per unit path length at a given wavelength or wave number. Part 2 of 3, Matching Filter Properties to the Gas. First, select Filter in the top menu and then follow these steps. Step 1. Download the provided list of standard IR filters here, or use your own filter list. From whichever list you use, obtain the value for the central wavelength, the CWL, and enter it in the CWL field. Alternatively, you can enter the central wave number, the CWN. If you enter one, the app calculates the other automatically. For today's example, we'll use a CWL of 4,260 nanometers. Step 2. Enter the half bandwidth from your filter list in the bandwidth field. In this example, we'll use 120 nanometers. Step 3. Enter the filter's maximum transmission value, Tmax, from your filter list. In this example, we'll use 80%. Step 4. Select Apply Filter. A new black curve will appear on the spectrum. This is the simulated filter transmission curve. Use this as a visual check to confirm the filter is positioned correctly relative to the absorption band. Make sure the bandwidth is not too narrow, but keep in mind that manufacturing constraints limit how narrow filters can realistically be. In many cases, it's safer to choose a filter that is slightly too wide rather than too narrow. Also remember that other gases in your application, such as CO, may show absorption features in the same spectral region, which can influence filter selection. Part 3 of 3, Simulating Measuring Distance and Concentration. First, select Simulation in the top menu and then follow these steps. Step 1. Enter the minimum and maximum concentration range in volume percent. In today's example, we'll use a range from 0 to 20 volume percent. Step 2. Enter the path length. This is the absorption length of your gas measurement cell, the distance the light travels through the gas from emitter to detector. For our example, we'll use 0.5 centimeters. Step 3. Choose the number of sampling points for the concentration sweep. This determines how many discrete concentration values the app will calculate within your selected range. More points improve resolution but increase computation time. For our example, we'll use 7 points. Step 4. Select Compute Simulation. The app will display a graph of absorption percentage versus concentration. This is your absorption curve. Aim for good resolution and good linearity in the concentration range that matters most for your application. Outside that range, linearity is usually less important. This is also a good time to test alternative filters to see which option best fits your requirements. If you have questions or would like support, feel free to contact the experts at Microhybrid. A screenshot of your simulation settings and results can be very helpful when reporting issues or requesting guidance. And to explore Microhybrid's NDIR measurement solutions further, visit our online shop at shop.microhybrid.com.